whole chapter has been about what derivatives tell you and the information that you can get if you're given a derivative. We can find maximums and minimums of functions. We can find concavity. We can also find some approximations, and this will be on the exam. It's actually more day 2 than day 1, but it all is the same thing. Okay, so what we had here before, we had the derivative operator of y with respect to x. And we called that just the slope, right? So that's equal to m. And actually we wrote it this way, dy dx is equal to f prime of x at some particular place. Yep, because this is what the slope is. Slope is f m prime. I now want to think of the derivative in a different way. This is slope. And if you think about it, it's the slope, it's the limiting value using the definition of a derivative. We had f of c plus h, but we also had this. We had f of x minus f of a all over x minus a, and we had x approaching a. Do you remember that? It was just the slope of the line. Well, this is really the change in the y values. That's why I like this form, and that's the form you probably will see in physics more often than the f of c plus h form. And this is just the change in the x values. And if x is approaching a, what's true about delta x? It's getting what? Smaller. So delta x goes to 0. And we call this the derivative of y with respect to x. So we can now think of this derivative as the ratio of these little differentials. It's called a differential. That's right there on the form. Where is it? The differential dx represents the change in x of both the tangent line and the curve. We'll get into that in a second. The differential dy represents the change in y along the tangent line. So there's my curve. I have a drawing. I actually put one on Inspire because I could change color, but I couldn't figure out how to change the color. It's kind of silly. So here it is. I have my tangent line right here. And this is what you have to figure out. I don't think it's labeled. You'll need to draw a picture probably. I just did this for myself. So I have a curve, any old curve, it doesn't really matter. And I'm going to find a tangent line at a particular point, and I'm going to draw that tangent line. And you just have to know what these things represent. So delta y is the change in the y coordinates on the curve. I'll write it again. Delta y is equal to, if we call this one x1 and we call this one x2, how about that? Is equal to f of x2 minus f of x1. It's the change in the y on the function itself. But it's fixed point. I don't have anything in particular. So if you wanted to draw the secant line, you could. So all we're talking about when we say delta y is just the distance that the y changes. It's this length. Okay? Yeah. I just took any 2 points. I'm just doing it in general. This is not any particular function or anything. So it's the change in y along the curve, or on the curve. And if I draw the tangent line, which I did in red, then this distance is the change in the tangent line. Well, that's dy, because if I take this formula right here, will that help me? That's just the slope of the tangent line. And remember what slope is? It's rise over run. So the rise on the tangent line will be represented by dy. That's this distance. And the run on the tangent line is dx. Well, what's true about delta x and dx? Delta x is the change on the function. This is delta x, and this is also dx. They're one and the same. But it's dy, this little height here and this height here, are they the same? Tom, are they the same? No. But if I keep delta x pretty small, they're almost the same. So what I can do is use a little calculus and find that dy is approximately the change on the function itself. Pretty close, provided that delta x is small. And you say, well, why would I do that? That's actually how your calculators work. It's actually a preview into what we do in BC Calc. We're going to use a line to approximate this curve, because you know what? Remember, if we zoomed in close enough, we could make our curve look like a line. And so actually, I could find this value on this curve by just using the line, which is really easy, which is how your calculators work. They don't do e to the x. They do the linear, well, they do a bigger approximation than that. But think of that as just, they're looking at the line and they just find the value along the line, because it's close enough. Because the calculators can number crunch just arithmetic stuff. It doesn't know how to do e squared. So it does it a different way, and it does it using this concept here. So that's the reason. Generally speaking, you know, we would like to find the actual change in the function. And we have calculators, and we can do it because we do have calculators. But back when calculus was invented or whatever, discovered, I don't know what the right word would be, which was in the 1700s, they didn't have calculators. So they used the calculus to approximate the change in y. And we'll do some examples of that. Approximately. dy is this length right here. It's approximately, not equal. This means approximately. Pretty close, because what if I make delta x really tiny? What's the difference between the blue line and the red line here? Curve, I mean. Not much. I'm going to use it to make approximations. When they say estimate, that's usually what they're talking about. And you know what? You've already done some of this. We just didn't call it anything in particular. And we'll hit on it again tomorrow. So we'll have it, you know, you'll be hit on it twice. Okay, what is the slope of the tangent line? Well, that's f prime of x. That's one way to write it. What's another way to write it? dy over dx. Now you can't think of this as an operator. It is a derivative, but it's the change in the y's over the change in x's of the tangent line. Can you solve for dy? If you think of this as just a number, what would you do to both sides? Multiply by dx. And that's what we get. We get dy is equal to f prime of x dx. So the first part is kind of easy. You may not quite understand what you're doing, but it's easy to do. I'm going to move my answers here. There's where I wrote dy dx equals f prime. And then I solve for dy in that equation. And that's called the differential dy. And all it represents is the change in the height, in the rise, on the tangent line. Not the actual change in the function. And I know it's confusing. You just have to think a little bit. And they have right at the bottom, in summary, delta y represents the change in y along the curve, and dy represents the change in the tangent line. You might want to highlight that. I have highlighters too. So let's just do some problems. And I put on here, you check with the assignment sheet. I need to check with that too, because we're doing this in a certain order. Yep. The change in both the tangent line and the curve along the x's, how the x's change on that. If I look at this height, then I look at this change in the horizontal, dx and delta x end up being the same. I'll be drawing more pictures. Okay, Sam? Yes. No, is approximately equal to it. It's almost the same, provided that delta x is small. So we'll do some problems, and so you can really see it's actually a pretty good approximation. Depends on how fast that curve changes. This one's curve is changing pretty fast. But if I have it concave down, do you remember what happens when a function's concave down? It looks like this. It's increasing, but it's not increasing very fast. See what I'm saying? This is increasing, but at a slower and slower rate. Eventually it stops if you get it horizontal. And this is speeding up, right? You think about it, you're speeding up. Okay, so let's do a problem. So if we want to estimate the change in some function delta y, I'm going to move this. These are the problems you want to do. These are the problems that relate to this. How about I put this up here? I have it on the regular smartboard. Those are the homework problems that relate to this topic today, so you don't want to necessarily go in order. I think it's wrong on the yellow sheet. Yeah, there was. I put it up there. I found it there. It's not on the. It's when you look at the title, going across what problems are assigned. It's not there, but it was actually on the sheet itself. I know I was going to redo that one. It was a nice little problem too. No. 4-6, we have a worksheet. Okay. So if we want to estimate the change in our actual function, let's say we lost our calculator. We're what was the guy lost at sea? Tom Hanks. He doesn't have a calculator. He wants to find out how something's changed. Maybe the sea level. You know, you can do a little calculus and find it by approximating it by dy. So delta y represents the change along the curve. If I draw the picture, I don't forget. dy represents the change in y along the tangent line. They're not the same. Okay, example 1. You're going to have problems that look like this. Write this, the derivative in differential form. You could either use this little piece of information where we solved, we had dy is equal to f prime of x dx, or I can just do the problem and then solve for dy, which is how I'm going to do it. We have to get this idea of differentials because they're going to come into play later on when we find antiderivatives. So what's dy dx? It's 2x. Now, think of this as the change in y over the change in x. That's of the tangent line. Can you solve for dy? Multiplied by dx. That's all, whoops, it's a d. That's all it's asking us to do. I'm going to fix this, though, so it looks right. Whoops. That's it. That's the answer to the question. So if they ask you to write a derivative in differential form, that's what they're asking you to do. So we're having two meanings. Before it was an operator, now we're looking at this as a ratio of the change in y to the change in x on the tangent line, not the function. That's it. That was easy. If they ask us that question, we can do that, right? Okay. Now the next question is one of those ones with a zillion parts to it. So first we're going to find dy. We're going to actually graph this so we understand what we're doing. I think that helps. Now I also put a little note here. It should say Friday. Tomorrow. Tomorrow when I do linearization, you can do it one of two ways. You can use what we did today, or you can use the equation of the tangent line. It makes no difference. We're just going to actually do this one. Okay, so let's graph that. Y equals the square root of x. Wish we had our math stuff, but we don't. Remember what this one looks like? It's a curve, right? The domain is just the positive numbers. It's the root. Is that crooked? Okay, so there it is. And I want to find the differential dy. Yeah, I thought so. It'll drive me nuts. There we go. Okay, and we're going to do this at x equals 1. Well, let's first do what it says to do. Let's find the differential. Let's just doing some work. So I have y is equal to x to the 1/2 power. What's the derivative of that? 1/2 x to the negative 1/2. Well, I don't like the way that looks. Do you? You like that? I don't like that negative 1/2. So dy over dx is equal to 1 over 2, and this is the square root of x. Is that okay? And then I want to solve for dy. I want this guy by itself, so I'll multiply both sides by dx. It's just the derivative of the function times dx. I like this because I see it happening every time. You can either memorize that little formula or you can just do the problem. Without the visual, this would not make much sense to me. Question. That's just I'm writing the derivative in what they call differential form. It's a definition. So I solve this equation for dy, and I get dy equals this. What is this? 1 over 2 squared root of x? That's f prime of x dx. Well, I'm going to work with that. That's the picture of the curve. So now, that was A. So this is part A. So let's do B. It says, find dy and delta y. I'm going to start at x equals 1. And I'm going to make dx and delta x be 1. And by the way, these do have signs to them. If dx or delta x is positive 1, that means we're going to go to the right. If I made it negative 1, we would have gone to the left. So they are directed distance is what we call it. Okay, so at x equals 1, how about if I put it right here? I'm not drawing to scale. I hope that's okay. And I want to find dy and delta y. And delta x and dx are both 1. So where am I over here? If delta x equals 1, where am I right here on the axis? 2. So I really want to find the actual change in y value here. So this ordered pair is 1 square root of 1. And this ordered pair is 2 square root of 2. Right? First do the thing we already know how to do. So what's delta y? It's the change in your y coordinates. That's all it is. It's the change in the y values. So what do you do with those to find the change? Subtract them. Square root of 2 minus, there's no calculus here, square root of 1. That's equal to the square root of 2 minus 1. And you guys know approximately what the square root of 2 is? 1.4? So it's approximately, I'm going to better put approximate symbols in there if it's not right, 0.4. It's actually 404. I haven't done the tangent line yet. I can't hear you. Okay, it says C, sketch the diagram. Well, you know what? I like to do it right away. I now need to find dy. Well, dy is the change on the tangent line. So I'm going to draw the tangent line. Try. Ugh. It's going to be thick. Okay, here's the tangent line. So now, the change on the tangent line is this. This is dy. You see that? Which is bigger, dy or delta y? Here's delta y. Is that an overestimate or underestimate? Because they're going to ask you this. If I go along my tangent line up to here to try to estimate that y value, is it going to be too big or too small? Too big, because this lies above the curve. Just look at it geometrically. This value is bigger than that value. So I want to find out what dy is. This is the exact answer, more or less. Let's find dy using the calculus. And where are we starting with our x's? We're not starting at 2. We're starting at what? 1, because I can find the square root of 1. Okay, so let's do that. So what's dy, just plugging it into my formula, is 1 over 2, the square root of where I drew the tangent line, which is at 1, and how big was dx? How big is the tangent x? It was just 1. Can I do this without a calculator? Yeah. This is what? 1/2 or 0.5. Well, that's clearly bigger than 0.404. But you know what? My delta x wasn't very small. That was really big. I want delta x to be like 0.1. That's not a bad approximation, is it? What do you think? This distance is 0.5. This distance is approximately 0.4. My delta x was not small. My delta x was big. If I made my delta x 0.1, now you're looking at the differences here, which is a lot, in fact, not even that big, which are going to be almost exact. But then I'll need a calculator. I chose this so I wouldn't have to. And then it says approximate the square root of 1.1 using differentials. I just like to use the geometry. Oh, I want 1.1? No. Oh, maybe I do. This was the square root of 2. What's the square root of 2 using differentials? Remember, this height here, this total height, is the square root of 2. Okay, what's this height right here? We see geometry now. This length is 1, right? And then you have to add in, so it's equal to 1 plus, and we want to approximate it. I mean, I know it's 0.404, but it's plus this little dy. So it's approximately 1.5. So that's a pretty good estimation, but it's too big. So I want to do the square root of 1.1 using differential. So let's go back and draw another picture. But let me add, now let's add another page. So f of x is equal to the square root of x. And I want to find the square root of 1.1. I'm still going to need a calculator, you guys. Sorry about that. But and what is it? Does anybody have their calculator out? What is the square root of 1.1? I don't know how big that is. Got to keep in mind, they did this back when there were no calculators. They didn't have calculators till 1973. 049. Okay, that looks good. So let's go ahead and draw the picture again, because that's the way I do the problem. You don't have to draw the picture, but I think it's easier. And I want to find, if this is 1, I'm definitely not drawing this to scale, and this is 1.1. I want to find an approximation to that y value. I'm going to use the tangent line. And I'm not going to try that big thick one again. Okay, so I'm going to do this. And look at that. Is that an overestimate or an underestimate? Over. So I'm going to have this height. Well, I know that height. How big is this right here? This ordered pair is 1 comma what? 1. Okay, Alex? And all I have to do is add 1 plus this change in y. Well, I don't know what the change in y is. The exact answer is 1 plus delta y. But I'm going to do 1 plus dy. Okay, so where's my x value? X is equal to what? Where am I drawing the tangent line? At 1. What's delta x, which is also the same as dx? That's 0.1, right? This distance here is 0.1. And you remember, we can go back, but I remember that dy was equal to 1 over 2 square root of x dx. Are you okay with that? Just me importing it in from the previous problem, because it's the same thing, right? So let's go ahead and find out what dy would be if you keep dx really small. It's 2 times the square root of of 1. Oh, it's not bad. Maybe I don't need a calculator. And what's dx? 0.1, right? So dy is equal to 1/2 of 0.1. What's half of 0.1? It's 0.05, right? So that when I use this distance here is 1. I hope that's okay with you. This distance to the tangent line is 0.05. So using calculus, I get an approximate answer of 1 plus 0.05, or 1.05. How does that compare to the exact answer of 1.049? Really good, isn't it? I didn't have to use a calculator. There were no calculators in the 1700s. Not until 1973 did we actually have calculators. We used slide rules. And I don't know when slide rules came out, probably 40s or 50s. That'd be interesting to find out. I don't know. Before my time, I grew up with them. And before that, we had an abacus, which are actually very good. Winfrey, can you use an abacus? Did you learn how to use one of those? Abacus is with the little beads to do your arithmetic. Oh, are you good at it? Yeah, that'd be kind of fun to bring one in and show, because people can do their arithmetic on abacus faster than you can do it on your calculator. Very, very fast. Okay, so that's how we do that. You got this as a model now. So now let's go to the last problem. Why do I use this? Here's another reason for using approximations. I'm a machinist. Okay, I'm building something. And by the way, this is a standard, an 8th grade algebra standard. I'm not saying it's appropriate, but it is a standard in 8th grade to find this error. Okay, so I have a circular disc, so I'm going to draw a little picture. Pardon? What's wrong? Oh, yeah. We decided we should have an AP algebra class. Okay, there's my circular disc. Not great, but it's okay. And it has a radius of 24 centimeters. We're going to get more into geometry now in next semester. I love geometry. Lots of geometry. So, geometry. Areas of trapezoids, triangles, and volumes of circles, washers, and such. Now, when you make this disc, for whatever reason it is, nobody's perfect. You guys know this from science class. There's an error, right? Okay, yeah, that's supposed to say error. I fixed it on the original slide, but not this one. But anyway, so I want to find out how will my area, what kind of area will I have, what kind of error in my area will I have if I have an error in my radius? So the change in the radius is 0.2 centimeters. So I could have a disc where the radius is equal to 24 plus 0.2, or the radius is equal to 24 minus 0.2. I'm okay. The specs say I'm okay if I only make 0.2 of a centimeter error in my radius. So then what would the corresponding error be in your area? Well, what's the area of a disk? Pi r squared. Okay, so if you want to see the error in the area, you would find the area evaluated at 24.2, and then you would find the area at 24, and you would subtract them. Now, I know what 24 squared is. Does anybody else? It's the same distance, though. It's the same value, so it doesn't matter. No, it's the error. The error is talking about how far off you are from the actual answer, which is 576 pi. And I don't know, what's 24.2 squared? Now I need a calculator. And honestly, I will get out of my desk to get a calculator because I don't want to multiply 24.2 times 24.2. Does anybody have that one? It's the same subtraction error. So I don't have to go the other way. If you wanted to do the distance between the two and cut it in half, you can. The error is defined to be how far you are away from the actual. It's the same distance, though. When you do 24.2 minus 0.2, 24 minus 0.2, and you subtract them, you get the same answer. So the error is always measured by the error here from what you actually want to have. What is that? 24.2 squared. Jason's got a calculator. 585.92. Well, whatever. I have to use a calculator, that's the point, right? And if we subtract those, what do we get when we subtract them? How many pi's? If I want the actual answer, I'll have to actually multiply by pi. So what's the difference there? I don't know what the decimals are because I couldn't hear it. 85 minus 76 would be 9, right? 9.94 pi. Okay, that's the error. They're saying that's okay. Okay, so let's now do this with the calculus. Because the area is equal to pi r squared. Delta A, that's the error. The change in the actual area from the original amount to whatever the error gives me. So if I could find dA, that will give me the approximate error. Is it good enough? Can I do this in differential form, or do you want me to take a derivative? What's the derivative of area with respect to what variable now? Not x. What's the variable here? R. What's the derivative of that? 2 pi r. Does anybody recognize that? You need to recognize that formula. That's the circumference. And they've had it problems on the exam when they show something as the circumference when they talked about area. So you have to recognize that that's circumference. But we're going to leave it that way. So what's dA, which is 2 pi r times dr? Well, what's the radius on a perfect disk? It's what, 24, right? What's the error in the radius? 0.2. And we can multiply that out. We can even multiply it out without a calculator. 2 times 24. It's 48 times 0.2 pi, or 9.6 pi. That's using calculus. This is the exact answer, 9.94. Pretty darn close. And notice this took me a lot more effort. And if I do volume, we're talking about cubing R. And 24.2 cubed, I definitely don't want to do without a calculator. Remember, you've got to keep in mind when this is all figured out a long time ago. But we can extend this. That's next year. It's, what is it? Oh, it's better than that. 5.6 pi minus 576. Darn. I'm sure there's some decimals out there that aren't the same, but that's really close. So when you take the test on this, we will ask you to do differentials. Yes, you could find the actual change in the area. That's not what we're asking. We're saying use differentials to do that. I know you know how to find the change in A. You use a calculator. But over here, I didn't use a calculator at all. Yeah. That's the exact change in the area. dA is an approximate change in the area. Right. I know it's not exactly the same, but it's pretty darn close. You got to give me more decimals. But you can go put it on your calculator and find out. Right? I think, are they the same as what we had before? Okay. But you know what these are? Those are the practice AP and the practice ACT problems. They're kind of important to do. Yeah.
Which one of these answers is like the relative or the percent?
I haven't done that. This is the approximate error. So how do I find the relative error? I take 9.6 pi and I divide by the actual area. So I do the change in the area over the actual area. Am I right, Haley? 576 pi. Pi's will go. What is 9.6 divided by 576? I want 3 decimal places, at least. Maybe more. 0.017? Okay, that's the relative error. What's the percent error? You multiply it by 100%, which is 1.6 repeating percent. It's almost 2%. Now, if you're selling iPads and you have a 2% error rate, meaning that the iPads are not going to be functioning, that means out of 100 iPads you sell, 2 are going to not be working correctly. Is that good business? No. So it depends on what you're doing. You have to look at that percent error to see if it's reasonable or not. Yeah. Well, if I'm flying in their aircraft, it better be pretty close to 0. But that is called a tolerance, is what this is. So this part will work, provided that we're less than 2% error on the area. But you always have to look at that. So if you're doing any kind of sales or stuff like that, financial stuff, you have to look at that error. And they use calculus. So if you're going to go into business, you have to have business calc.
So when we estimate the maximum error, we're always going to have 2 answers?
No, there's only one answer. I did it 2 ways. This one, let me label this. With the exception of the fact that there's more decimal places, this is the exact. This is approximate. The point is, we want to be able to do it approximately because it's easier. This was a lot easier to do than that. And some of you are saying, I got a calculator, it's really no easier. Could be on the non-calculator part of the exam. Then it's easier. If you're doing a lot of calculations on the non-calculator part of the exam, you're doing something wrong. I've seen people do that, cover their page with calculations, but no, no, no. Because without a calculator, they're not going to make the calculations hard. This is just another application. Tomorrow we'll write the equation of the tangent line and do, it's very similar. It's not that different. So now, if we want to look at some of the problems out of 4-4 that we assigned, or we could look at that problem 4 out of that worksheet. Now, we could do number 6 if you'd like. Yeah. And then I put up 22. Mrs. Hersman did 22, but she did the hard way. So you can look at both and maybe tell me why her way is the hard way. And she just plain did the problem. And she didn't stop and think, oh, how could I make this a little bit easier for myself? And then I put up 41. And 41 is a nice little problem. So let's look at number 6. I want the largest rectangle. A rectangle has its base on the x-axis and the upper 2 vertices on this parabola. Well, I better graph this thing. My parabola is 12 minus x squared. Is that odd or even? Okay, guys? Is that an odd or even function? It's even. And when x is 0, where's the y value? The 12. What's happening with my parabola? Opening up or opening down? Down. And it's symmetric around the y-axis. It's an even function. Okay, what are we going to do? Okay, the rectangle has the base on the x-axis, and its upper 2 vertices are on the parabola. So it's going to look like this. Oops, that's supposed to be a straight line. Kind of saggy.
I can tell where the points are.
Because it's an even function, it's symmetric.
What? This?
They're always going to be like this, and they should have really told you that.
How up far?
I don't know where that is. So why don't we call this x? Now, I don't want to call the whole base x, because x actually is the coordinate. If the whole base is x, it's no longer the coordinate. So if this is the distance from the origin, what's the height of this? What's the y value here? 12 minus x squared. Because they tell you, they gave you the formula. So if I go over 2 units, for instance, I can find the height by plugging in 2 there. Well, I'm going to plug in x. Then what's this distance? It's the same. And this is y. And what's y equal to? 12 minus x squared. It's argued in a couple different ways. We'll call that the y. And it's measured from the origin. So it's okay. And so I want the maximum area. So what formula do I want? Of the rectangle. What's the area of a rectangle? Length times width. What's my length? Look at the picture. It's not x. It's 2x. And the height is, or the width, is the y value. But I know what y is. Thank goodness they gave me what y is. It's 12 minus x squared. Does that make sense? So that the area is equal to 2x times 12 minus x squared. I'm convinced you can multiply that out and get the derivative. I don't think you should have any problem with that. It's a nice continuous function. Is it a closed interval? Okay, Alex, what's x going to be? What's the smallest x could be? You could have a rectangle that looks like this. See, there's a lot of them. What's the smallest x could be? Must be greater than or equal to 0. And then the biggest one you could put in is this one. I'll color that one in. When y is 0, right? Y must be greater than or equal to 0. But what's y? 12 minus x squared. Okay, they could have given us a little bit better numbers, but they didn't. So 12 minus x squared must be greater than or equal to 0. So 12 must be greater than or equal to x squared. I don't like my inequality in that order. So guess what I'm going to do? I'm going to flip it. X squared is less than or equal to 12. When you square root that, That's okay. What is the square root of x squared? It's not x. The absolute value of x. Square roots are always positive. And absolute value of x is the square root of 12. But remember, x has to be greater than or equal to 0. What's the biggest value it's going to be? Smallest value x can be a 0. Can't be negative because x represents the distance from the origin over to the curve. What's the biggest it's going to be? Square root of 12. And when I get these max-min problems on a closed interval, I like to draw a chart. I just love to draw the chart because then it's easy. So I need to evaluate my area at my critical points. I've got 2 critical points. Are you starting to see the max-min existence theorem a little bit more? Where's my other critical point? Where the what? Where the derivative is 0. So guess what I have to do? I have to find the derivative. Now, some of you will find the derivative as written, which will be a lot of work. And some of you will say, why don't I just distribute that? Because that gives you 24x, read that, minus 2x cubed. So now we can find the derivative easily. Now the calculus is easy. Doing the product rule wasn't easy. So what's this? 24 minus 6x squared, and I want this to be 0. I get another radical. So 24 equals, 6x squared. Question? Right? Sorry. Well, I put the 6x. Let me put the 6x squared on the other side. Then we don't have to worry about the signs. So I'm going to add 6x squared because I'm going to get the same thing. If I had negative 6x squared, I'd have negative 24. So x squared equals 4. And x has 2 values, 2 or minus 2. But look at our interval. Our interval goes from 0 to the square root of 12. X can't represent a negative number. So we got to get to throw that one out. Now I'll draw my little chart. Doesn't work. Oh, almost. Okay. So here's x, here's my area. My endpoints were 0, square root of 12, and my other critical point where the derivative was 0 was 2. And my area was, I like to keep it in factored form personally, 2x times 12 minus x squared. Because these are my endpoints. There's just many steps. I think that's what makes this one kind of hard. This is where f prime equals 0. So what is the area if x equals 0? 0. What if x equals the square root of 12? Because this gives me 0. So that's 0. Obviously, that's the minimum area, right? Therefore, this must be the max. Because the max-min existence theorem guarantees both a max and a min if you have a closed interval, which we do, and a continuous function. And the only candidates are when the derivative is 0. So Michelle Bachmann is out of it because the derivative's not 0 or undefined there. She's no longer a candidate. Well, I got to go back and look at the question. If they just say where, I'm done. If they say what is the maximum area, I'm not done. So let's look at the question. What are the dimensions? So I wouldn't even bother finding the area. I'm done. I know that's the maximum. So x is 2. Now we got to be careful. Let's not make the mistake I made yesterday. If x is 2, the dimensions are 2x by y. Oh, I don't like that. I'll do it that way. Well, it's 2x. X is 2, so this is 4. So this length is 4. What's y? 12 minus 2 squared. So it's 4 by what? 8. And then I could answer the question what the area is. If I really want to make sure that I'm going to get all my points, 32. But you can say max-min existence theorem and you're done. I should give you copies of last year's. Some mean value theorems in there. I'll have to look that up. I don't know if I have any, I don't have a prep hour today, but we'll see what I can find. Okay, is there another one you wanted to look at? We only have 3 minutes. And no, did you look at my solutions online? I don't like to write small. Took the whole page. Let's set up 22. Because 22 is tough. We got 3 minutes. 22 is talking about a cylinder and a sphere. And the question I had when I first looked at it is going, okay, what are we trying to maximize? It's always the problem. So 22, maximizing the volume. Find the dimensions of a right circular cylinder of maximum volume. Okay, here's my cylinder. What's the volume of a cylinder? They will give this to you, by the way. This will not be anything you have to know. It's the area of the base times the height. So that's pi r squared times h. And I'm going to put that in a sphere. Because time constraints, I'll have to draw it. And I'm going to put my cylinder in here. This is what they mean by a right circular cylinder. And I want the biggest volume. This tells me I need to find the height of my cylinder and I need to find the radius. So let's start at the center. And it says the sphere has a radius of 10. So if I draw this, that goes to that edge there, that's 10. And I call this r, the radius of my cylinder, and I'm going to call this segment little h. There's a relationship there. What is it? It's Pythagorean theorem. R squared plus h squared equals 10 squared. Now, how big is capital H? If little h is here, what's capital H? 2 little h's. So my volume equals pi, this is the hard part, r squared times 2h. I either eliminate r or eliminate h. Mrs. Hersman chose to eliminate h. I chose to eliminate r. Because what is r squared? It's 100 minus h squared. So it's easier. Pi, it's 100 minus h squared. And then what are you going to do with the 2h? You're going to multiply all that out. Take the derivative, a nice continuous function. Is it a closed interval? Well, what's the small? Here's the smallest radius I could have for my cylinder. What does r have to be? Well, that doesn't help me. R has got to be positive. What about h? H has to be positive, right? What's the biggest little h can be? What's the biggest little h can be? If you make it, yeah, it's 10. It's got to be, little h has to be less than or equal to the radius of the sphere, called capital R. So h is less than or equal to 10. So your closed interval is 0 and 10. Now I've done almost the whole problem. So you can try the other ones, and I don't think it's too bad an assignment for 4.5. At least I hope it's not. Shouldn't be. And then we'll do tangent lines tomorrow, and then next week we'll do what they call related rates. Those are kind of fun, actually.